Hi everyone, it's Sorkin. Today we have a problem where we need to design a data structure that supports adding in new words and finding a string that matches to the previously added string. So basically finding those words. So in our case, we are going to implement a class word dictionary, and it will have two functions. Add word function, which is returning void. We are just adding the word to our data structure. And we also have a function search, which is returning boolean depending on whether that word exists in our dictionary or not. So also we have another requirement. If the word that we are searching, right, if it contains dot, it means that it can be replaced by it can be matched by any character. For example, in case, let's say that we have added math to our dictionary and we are searching for the dot and the AD, that it should return true because the first character doesn't matter, right? It can be any character. And also we are given an input. We are calling the add function 3 times. We're initializing our object and we are calling the add function 3 times. We are adding bat, that, and the mat, these three words to our dictionary. And then we are calling search function on these 3 words, right? So for example, the first one is the pad, right? Pad does not exist in our dictionary, so we are returning false for this case. So how about the bat? Yeah, bat exists in our dictionary, so we are returning true for that. And how about the next one? Next one is that the dot and the AD. So all the words that we have in dictionary, it matches our search, so we are returning true in this case. The last one is it starts with the B. We have that, and the 2 dots, which means that the rest of the character, that doesn't matter, the size should be 3. So we have that word and we are returning true also in this case. Okay, the data structure that we are going to use in this case is trie, and let's implement the trie. So how we are going to implement the trie? So let's visualize that. So the root of our trie doesn't matter, so we are going to use just add the dash here, and we need to add 3 words to our trie, right? Bat, dat, and mat by requirement. So let's take the first example that we had. So we are first adding bat, right? We are adding B. So we are adding character by character. We are adding A, and we are adding D, right? We are adding D. So also the next one is that, right? We are adding D here, D, A, and D, right? That. The next one is the last word that we have is mat, right? Mat. So mat, M, A, and D, right? So why the trie data structure is convenient? Because for every character, right, there could be no more than the 26 possibilities, for example, meaning that the letters of the alphabet. So for example, let's say that we want to add one more word here. We want to add one more word to our dictionary. Let's say that outside of our example, right? So let's say we want to add map, right? So we are adding map here, we are adding P here, right? And we are adding that to our dictionary. How about the next one? Let's say that we want to add one more, right? We want to add mall, right? Mall to our dictionary. So in that case, we are adding L and L, right? We are adding mall also to our dictionary. So searching for the word, searching for the word is much convenient in case of the trie data structure. So that's why we are using the trie in this case. So let's take our example. Our examples, which are our example? Our example is pad. Our example is bat. Our example is dot, add, right? And our example is B and the 2 dots. So let's search for those words in our dictionary. So first one for the P, right? So we are searching for the P. There is no character that starts with the P with the first letter, right? So we are searching character by character. There is no word that starts with the P, so we are returning false in this case. How about the bad? For the bad, so we are searching for the first word, for the first letter, it exists. So now let's compare the second one, this one and this one, right? Yeah, they are equal. And how about the last one? D is equals to D. Yes, it equals, and we are returning true for this case. How about the dot and at? So we are going one by one, starting from the first letter of the alphabet, right? We are starting with the B. And in this case, so we are comparing again. So dot, it can be any letter. So we are taking this one, right? It can be any letter. So we are going to the next character. Next character, does it match? Yes, it does. So we are going to the next character, and we are comparing the next character. D is equals to D. Yes, it equals. So we are returning true in this case also. How about the last one? Last one is the B. It should start with the B. So we are again going to this branch, right, where it starts with the B, and we are going to the B is equals. Yeah, B is equals to B. We have the B in our dictionary, so we are going to the next one, and it doesn't matter if we have two letters in our dictionary, so it doesn't matter. It could be not, for example, not bad. It could be something like something like a B, let's say, right? Let's say it could be B. Let's say that this one does not exist, right? And we have here B, right? E and E. So we have a B here, and so in this case, we are again returning for this scenario, for this particular scenario, we are returning true. Okay, let's take a look how exactly we are implementing our try. The first thing that we are doing here, we are adding our inner class try node, which has three fields. First one is that the data, where we're storing our data. The next one is the Boolean is and. It represents that is it the complete word or not. So for example, let's say that we are adding map. We added first character M, we added A, and the last one we are adding P. When we are adding P, we are marking this as true because at that point it's a complete word. And another one is a children with the array of try node with the size of 26, one for each character of the alphabet, right? Then we are initializing our word dictionary. We are not in our constructor, we are passing no arguments here. And the next one is we are implementing our add word function. So what we are passing here, we are passing word, and now we are starting to add that to our try. Let's say that we have here map. We are adding map here, right? So we are adding character by character. First we are adding M, then we are adding A, then we are adding P. So let's say we are adding M. Now we are checking. So this is the first word that we are adding to our try. We are checking in our try. Does that M exist in our try? No, it does not exist. Why we are minus A? Because 0 A we are going to store. Why we are taking minus A character here? Because in the 0 we are going to store A character, in the 1 we are going to store B character, and so on. In the index 1, index 0 we are going to store A, index B we are index 1 we are going to store B character, index 2 we are going to store C character, and so on. So we are checking if the M exists in our try. So if it does not, then what we do, we are creating a new try node, and so we are setting that our current children, so at M, right? So we are creating a new try node for it because it does not exist. If it exists, let's say that we have added another word earlier. Let's say that starts with the M. Let's say man, right? We have added earlier. And in that case, M already exists in our try. So we are just pointing that to the M. So we are pointing to the M. Now, then we are adding each character. After adding M, now we are pointing to M. So now we are the next one is we are adding A right here. We are adding A here, and when we are adding A, we are again checking that if it exists or not, because in our case, since we are adding map for the first time, A also does not exist. So we are also creating a new try node for the A, and the same we are doing for the P. Once we add the P, so the last character, right? So we are, as we exit this loop, we have added all characters. We are adding is and for the P as true, because this is complete word. At this point, it's a complete word. Okay, this is our add word function, and the next one is our search function. What we do in our search function, so we're creating another search function, and the passing, because we are going to pass 3 arguments, and we are going to call that function or method recursively, so that's why we are creating another search method, and we are passing word, we are passing index, and we are passing our root. So what is the base case for us? Let's mark it here as a base case, right? What's the base case? The base case is that, so if let's say that our word is the word that we are searching is, we have added map, right? The word we are searching is AP. So by default, we can have, by the requirement, we can have a dot which represents any character, right? So let's say we are searching for the A and the P. So if our index is equals to 3, so which means that we have recursively called 3 times and we increased our index, it equals to our word length, then in that case we are checking if our root is n, so which means that if that is a complete word. For the P, right, it's gonna be true, so we are checking if that is true, then in that case we are returning true. So and if the index is equals to word length and the is and is not equals to true, then in that case we are returning false. So this is our base cases, and now let's look at the recursive call of the function. What's the recursive call? So at this point, what we are doing here, so first we are checking that if it's a dot, it means that it can be replaced by any character. We are skipping that character, and we are checking any children that is not equals to null. Or let's say that we are for the AP, right? So let's say that we have some other word, right? Let's say that we have added earlier, let's say bad, and we have 2 words. We have bad and we have map that we have added to our dictionary. So we are gonna first check for the B, right? If it's not equals to null, so B is not equals to null, so index 1, right, is not equals to null, and we are recursively calling and recursively checking other indexes. So at this point we don't check is it exactly equals to our index or not, right? So because it's a dot, so it can be any index, so it can be any character, so we are just recursively calling. And if that is true, so if that returns us true, so let's say that if this function returns us true, right? So then in that case we are going to return true also here. So how about the next case? The next case is that when the character is not equals to dot but equals to character. So in that case we are exactly checking that if that character exists if that character is not null. So if it's null, right, then we are not, so if that character does not exist, let's say that we are searching for something like, let's say we are searching for something like table here, right? Table. And we are checking for the first character, T. T does not exist in our try, right? So what we are going to do, we are just going to return false because T does not exist. So if it exists, let's say that we are searching for A and P, not for table, for A and P. We are going to, or let's say we are searching for bad, right? So we first checking that the B exists, then we are recursively calling function, then we are checking that is A exists, then we are recursively calling function, and so on. If it does not, so again, like in case of the table, right, we are returning false here. Okay, so this is the 2 implementation of our trie data structure. What's the time and space complexity of this solution? Time complexity is of n, right? N is being the size of our word, added word, and the same for the space complexity. In the worst case scenario, we're gonna add all the characters, right? Let's say that in some cases we may not add all the characters because some characters may exist already. But in the worst case, we're gonna add all characters, so it's gonna be also of n. Okay, that's it for today. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.